Bismillahirrahmanirrahim. Okay, so today our topic is the concept of the chromophore in the UV visible spectroscopy or the auxochrome. Fine. So when we talk about these two terms, so definitely the thing that comes down in the UV visible absorption of radiation. So since we are dealing with the UV visible absorption spectroscopy, the concept of chromophore, as the word says, is chrome, that means color. So chrome means color. Just like chromatography, that's color, something to do with the color. So chrome basically means color. So basically these are the functional groups, these are the subatomic entities present in the molecules, are present in the materials which are responsible for color. मॉलिक्यूल्स में जो कुछ स्पेशल फंक्शनल ग्रुप्स होते हैं या फंक्शनल एंटिटीज होती है या कुछ ऐसी साइट्स होती है, ओवरऑल ऐसा स्ट्रक्चर होता है कि दैट एक्चुअली इज रिस्पॉन्सिबल फॉर कलर इन द मॉलिक्यूल्स. सो क्रोमोफोर इज अ फंक्शनल ग्रुप और इट इज अ मॉलिक्यूलर एंटिटी और इट इज एक्चुअली, अब तो ये ब्रॉडर टर्म में ऐसे यूज करते हैं कि इट इज द स्ट्रक्चर ऑफ द मॉलिक्यूल, सो विच इज रिस्पॉन्सिबल फॉर कलर इन द मॉलिक्यूल्स. सो कलर इन मॉलिक्यूल्स, कलर इन मटेरियल्स or color in organic molecules, organic materials, organic molecules. So these are called as chromophores. ठीक. अब chromophores में, for example, अगर आपके पास ये एक ग्रुप है, take an example, understand the chromophore. If you have benzene, this is benzene, so it is colorless. Simple, in simple terms, इसका color नहीं होता, it's a colorless compound. If you do the nitration of this compound, if you add nitro group, you'll end up with nitrobenzene. Now this nitrobenzene, its color is yellow. Color is yellow, and usually the nitro groups, they are yellow colored compounds. So it turns out that this group is actually responsible for color in the compound, or this group is called as a chromophore. It imparts color to the compound, so this is called as a chromophore. Now what is the main thing here is that so this is the case of groups. Likely sometimes you may have presence of certain groups like let us say now this is the case of groups. Sometimes you may have the case where the compounds are conjugated. Sometimes you have a case like this, case where the compounds are conjugated. And then we have, this is 1,3-butadiene type compound, satisfying the valence here. So 1,3-butadiene type compound. And one more example I will put hexatriene. So this hexatriene. Now this compound, it absorbs, let us see, it absorbs around approximately, it will absorb around 217 nanometers. So that's in the ultraviolet range. Now this molecule, since it has one double bond, it has one more double bond, and you see that these are in the conjugation, alternate double bonds, they're in the conjugation. So you can have this type of conjugation, or you can have this type of conjugation. Now here the conjugation is more, you see. So this extensive conjugation, it actually brings the absorption towards higher wavelength. So this molecule can be around the 300 nanometers approximately. So this has a lambda higher than the previous one, that this is lambda 1. So lambda is higher than lambda 1. So it turns out that it is not the superspecific functional groups like nitro groups. It's actually the structure of the molecule. So it's actually the structure of the molecule that also imparts color to the compound, and usually that is the conjugation. When the molecules are extensively conjugated, that pi conjugation also imparts color to the compound. Or I can say now this also acts as a chromophore. So the extensive conjugation acts as a chromophore, it imparts color to the molecule, or there can be the groups present in the molecule that will absorb the radiation and impart color to the molecule. So they are called chromophores. अब देखिए इनमें एक अजीब बात है, यहाँ पे you have sigma bond, so that means sigma to sigma star electronic transition is present. Now you have pi bonds, so pi to pi star transition is present. Now this higher wavelength absorption, it is actually due to this pi to pi star transition. जैसे हमने पिछली क्लास में भी कहा था इलेक्ट्रॉन ट्रांजिशंस के बारे में कि this is a low energy transition, that means it absorbs in the higher wavelengths. Higher wavelengths means if the compound has to be colored, then that has the wavelength absorption should be higher. So those compounds are colored, there you have either this pi to pi transition, or if you look at this molecule, nitro has a lone pair, and then you have pi bond, so you have pi to pi star transition. You have also n to pi star transition. So here the n to pi star transition has an important role to play, the color along with pi to pi. So in the chromophores, the electronic transition that actually happens when it absorbs the wavelength, that is either n to pi star transition or pi to pi star transition. So these are the two transitions which actually occur in the colored molecules. So those molecules which they have the color, so that is because of this n to pi star transition, or that's pi to pi star transition. So these transitions, they impart color to the molecules. So the chromophores are basically the functional groups, are the structure of the molecule that actually imparts the color, and it results in the n to pi star transition or pi to pi star transition. So this is in general the concept of chromophores. Fine. Now molecules may have, for example, pi bonds present and extensively conjugated, so that can impart the color. Take sometimes it can be C triple bond N cyanides, type of functionality groups present in the molecule. So sometimes it can be triple bonds. They can also act as the chromophores. It can be sometimes carbonyl groups. It can be carbonyl groups. So these are called as the chromophores, which impart color to the molecules. Okay? So this is the general concept of the chromophores. They are the molecules which absorb the UV visible radiation, and they impart color to the molecules. And it is not necessary that it can be a specific group. It can be an extensively conjugated framework of single, double bonds, or double and triple bonds, or single and double bonds. So this is in general, in short, the concept of chromophores. Now when we discuss the color of the molecules, then there is another term that's called as the auxochrome. The auxochrome is closely related to the chromophore. So auxochrome is closely related to the chromophore. So auxochromes are actually not responsible for color, but what they do, they have an important role to play, is that they enhance the color in the molecules or materials. They enhance the color. So they are those entities which actually are not responsible for color, but they play an important role, they enhance the color. Or I can say, if a molecule absorbs at lower wavelength, because of the presence of this entity auxochrome, now it will absorb at higher wavelength. Now once it comes into the higher wavelength side, जैसे हम देखते हैं electromagnetic spectrum में you visible, then UV, then NIR, and then यहाँ से इस साइड में you can have X-rays. मिसाल इस रेंज में molecules absorb, it is responsible for color in the world, this range. यहाँ पे we will discuss Vibgyor, violet, indigo, green, yellow, orange, and red. So if somewhere a molecule absorbs in the ultraviolet UV radiation, and if there's an agent that you add to the molecule, and that agent actually pushes the color towards absorption towards the higher wavelengths. That will go towards the ultra visible region. That's the molecule becomes color. So this is the role auxochromes play. They enhance the color. They shift the wavelength from lower to the higher side. Now this shifting of wavelength from lower to the higher side because of the auxochromes. Now this is called as bathochromic shift. Bathochromic shift. Now there we have a topic, we'll separately discuss that. लेकिन अब यहाँ भी बात आ गई. और चूंकि for example initially it absorbs here ultraviolet, now it absorbs violet, or it absorbs towards green. Now it is going towards the higher wavelengths. On the higher side we have a red color, so it's also called as a red shift. Red shift. So the auxochromes, they actually enhance the color. They actually make the molecule to absorb in the higher wavelength region or low energy region. So they actually do the bathochromic shift or red shift, and this we'll discuss separately. Now we'll move back to the auxochromes. So auxochromes actually, they enhance the color. They make the molecule to absorb at the higher wavelength side. For example, now these groups are usually the groups which are auxochromes are amines. It can be SH. It can be OH groups. It can be sometimes this substituted amine. So these are the groups which actually enhance the color. So they are the auxochromes. The color enhancing groups. Sometimes can be halides also. For example, usually chloride. It can be iodide also. We'll take an example. For example, you have benzene. This absorbs around, its absorption wavelength is maximum absorption. Now before we start, what do you mean by this lambda max? So in the usual spectroscopy, when you use the instrument, if you look at a graph, finally, your piece will get a graph that is absorbance versus, this is absorbance A. This is the wavelength along the x-axis, wavelength of absorption in nanometer. Let's say it is 100, it is 200, 300, 4, 500. You see the graph like this. So this is the typical usable spectra. So at this point, now let us say this is 0.1, 0.2, 0.3, 0.4. So this point, if you see, this is the point where the molecule, it corresponds to around 500, and on this side it goes to 0.5. So this is the maximum absorbance that this molecule has. So this point corresponding to this wavelength where the maximum absorbance is called lambda max. Maximum absorbance corresponding to this wavelength called lambda max. And this is here in this case, lambda max is around 500. Same is the case, we have this benzene molecule. So benzene molecule has lambda max around it has around 255. Now 255 range, we know it's a ultraviolet range. We know ultraviolet is around it is around 220 to 380 nanometers. So it absorbs in the ultraviolet region, and its extinction coefficient calculated is around 203. 203 mole inverse and the liter or mole inverse decimeter cube extinction coefficient. Now in this group, if we insert NH2, so you'll get aniline compound. Now this molecule absorbs around, lambda max is around, in this case, 280 nanometers. And your extinction coefficient, epsilon, is around 1430. Now, if you see the comparison, when we're having benzene, at lambda max it absorbs around 255 lambda max, this point, and its extinction coefficient is 203. When we have amine group present, so its absorption is going towards the higher wavelengths at 280. And extinction coefficient is also increasing. So this group is called as auxochrome. Now, one may get confused, it can be a chromophore. So now this compound is not colored because absorption 280 is not colored. This is not visible region. But then it has made the molecule to absorb from lower region to the higher region. Sometimes it is possible that if it is 400, sometimes if it's a different molecule, it's 400. You add an amine group, now it goes to around 500. There the color will go from one, there will be one color transition from one to another color. But here is transition from one lambda max to another. So this higher wavelength side, this shift, this is imparted by the presence of a group. This is called as auxochrome. Then there is also the change in the intensities. The auxochromes are basically the groups which are not responsible for the color in the molecules, but they are the color enhancers, or they make the molecules to absorb from one wavelength to the higher wavelength. Or their extinction coefficient also changes because of the auxochromes. Okay? Now, we'll take one more example for understanding the part of auxochromes. So chromophores impart the color, and auxochromes, they enhance the color. Those entities, those functionalities, they enhance the color. Now, we take the example. So what auxochromes do? It's very important. What auxochromes do? Why they make the molecule to absorb at a higher wavelength side? So what they do is that, for that we'll take an example. This is a compound, I'm drawing it, a hypothetical compound here. A cinnamyl type 2 compound. So you have a carbonyl group here, you have a double bond here. So in this case you have conjugation because alternate single and double bonds. So you have conjugation. So now you can show it that molecule like. So now you have the poles in the molecule. Fine. The molecule is polar. So there's a delocalization present in the structure. Now if we have presence of some group, like we'll take another molecule. Same molecule are insert a group here. NRR group. Now we have similar delocalization here, but then what has happened? The positive charge was here, that is also getting stabilized by the lone pair. So now you have a case, the molecule looks like this. So plus here. So you have plus here. The double bond. So now you see here, and it has a pole here and then here. So there is more extensive conjugation. Now the charges are actually delocalized along a larger framework. So that means this group, what it has done, it has extended the conjugation. So that's what the auxochrome does, that it extends the conjugation. Okay? Extension of conjugation actually means the stabilization of structure. Stabilization. A molecule stable हो गया. Molecule stable means जो उसकी energy levels are there coming closer. Now इसमें we have oxygen, we have pi bond, so the wavelength, it is n to pi star transition here, which are responsible for lambda color absorption, of responsible for the lambda max, either it is pi to pi star. So these are the transitions. and here also similar transitions, n to pi star, pi to pi star. Fine. So these are actually the groups. Now these are the excited states. So what actually these groups do, they are extending the delocalization. With the help of that, they are bringing the excited state energy down. For example, if this was pi level, this level diagram, this is n, this is pi star. So the transitions are like this is pi to pi star, n to pi star. So what this extensive conjugation brings is that it brings these energy of pi star down. So now it becomes like, now look at the n to pi star transition. Now here it is n to pi star transition. N to pi star, it has gone down totally. Same is the case here. So it has gone down. Now when the energy gap is going down, now in the substituted molecule the gap is less. That means it will absorb a higher wavelength side. That's called auxochrome. So it brings the energy of pi star down so that n to pi star transition becomes easy, or pi to pi star becomes easy. That's why in the extensively conjugated molecules like butadiene, hexatriene, the wavelength is going towards the higher side because the energy gap between the two levels is going less. It will absorb at the higher wavelength side. That means it will go towards the higher wavelength absorption. Lambda max increases. So this is called as the red shifter. This is what we call as the bathochromic shifter. So this is what actually the auxochromes do. They enhance the color, they alter the energy levels, they bring the excited state down. That means the energy gap decreases. So this was in general the basic concept of chromophores and auxochromes. We'll again deal with this. For that हमारे पास जो topic होगा, that will be the bathochromic shift and the hypsochromic shift, or we can say the factors which will affect the U visible spectra, lambda max. वहाँ पे इसको हम इंशाल्लाह दोबारा डिस्कस करेंगे. This is all for the day about the chromophores and auxochromes.